Welcome to day 4, and we're going to look at the fundamental theorem of calculus, and this will be part 1 of 2. We're going to start off by doing a review. So for questions 1 and 2 on the very first page of your note sheet, I want you to try those on your own to review how to take the derivative again, and then to look at an application question like solving for displacement and velocity and acceleration of a particle moving along a line. So go ahead and do that, and then when you are ready, press play. Okay, so for question 1, we're just going to take derivatives of various functions, and this is because we're going to look at antiderivatives today, meaning that we're going to be given a derivative and then work backwards to get the original function. And this is what integration is all about. It's finding the opposite of taking the derivative, which is taking a derivative and going back to its original function. But for now, we're going to keep taking the derivative, going the forward direction. So this is your power rule for 1a. You bring down 3, which means you have 3 divided by 3, and that's 1, and then you're left with x squared because you subtract 1 from the exponent. The derivative of any constant number is just 0. For the next one, you'll just take the derivative of x, which is 1, and the derivative of sine x is cos x. For this next one here, the derivative of 3 to the power of x is 3x ln 3, but that ln 3 is going to cancel out with the 1 over ln 3, so you're just left with 3x. In D, the derivative of ln x is 1 over x. Here is x to the power of a half, so you bring down the half and subtract a 1 from it, which is negative a half for your power, and you can rewrite that as a fraction. Then the derivative of 6x is 6. For e, the derivative of e to the x is still e to the x. Your inverse tan derivative is 1 over 1 plus whatever it's going to be in the bracket there, which is just going to be x to the power of 2. Then lastly, derivative of tan x is secant squared x, and the derivative of secant x is secant tan x. So that is your review for derivatives. You still need to remember how to take derivatives and all of those library of derivatives that I've given you before. So question 2 is motion along a line, and we are given the function s of t, and this describes position. So for 2a, we're looking for the change in position, which is really your displacement from time 0 to time 2. So to find the displacement, this will be the change in your position from t2 to t equals 0. So we're just plugging in t equals 2, t equals 0 into our position equation. And then you'll do 2 to the power of 3 times negative 1 plus 6 times 2 to the power of 2 and then minus 2. And then do the same thing for 0, which is just minus 2. Simplify, you should get 16 as your change in position. To find velocity, we need to take the derivative of our position equation. So v of t is the derivative of this, so that's why we have negative 3t squared once you take the derivative. Bring the 2 down, that's 2 times 6 is 12, t. And then we'll plug in t equals 2 in this v of t equation, and then we're done. To find the acceleration, that is going to be v prime of t to get our acceleration. So we're going to take a velocity equation and then take the derivative of that. And if we do that, we get negative 6t plus 12. Then we want to evaluate this at t equals 2. So we plug in t equals 2 into a of t. For D, to find the average rate of change, your average velocity. In physics, this is going to be your change in position over your change in time. Or you can think about this in terms of slope as well. y2 minus y1 over x2 minus x1. So that's what we did over here. our change in displacement already found in 2a, which is 16, and then we know our time intervals from 0 to 2, so that's 2 minus 0. So your average rate of change for position is 8. Then it says integrate the velocity function, and then what do you notice? So we can just integrate this using our calculator if you want. So you can just put this v of t, which is negative 3t squared plus 12t, inside your graphing calculator so you can find the integral. And when you do that, you should get 16. The long way of doing it is drawing this parabola and then finding the area underneath, but that wouldn't be the best way with the methods we have so far, so it's probably easier for you to just put that in your calculator. And it says, what do you notice? So we do have 16 again in A, which was our displacement. So if we integrate velocity, we're going to get displacement. Just like how if we took the derivative of a displacement, we have the velocity. And lastly, we want to find the average value of the velocity function. So for average value, we're going to use a formula from the last lesson to calculate that. And that's 1 over b minus a. In this case, it's 2 minus 0. And our bounds are from 0 to 2 of our velocity function, which again is negative 3t squared plus 12t. And then you can plug this into the calculator again, or we also just solve for that in E. So we know that this part, our integral is 16, and then we're going to divide it by 2 because of the fraction in the front of the integral, which is 8. And if we take a look at this, this is the same as our average velocity that we found in D. Okay, so now we're going to look at the fundamental theorem of calculus, which has 2 parts. These 2 parts together is the concept of integration and differentiation. And it's one of the most important things in the discovery of calculus in mathematics. So let's look at example 1. This is a graph. It shows a velocity function for a particle moving along a line. Given the following, write an expression that will give you the change in position or the displacement of the particle. So to get our displacement, we need to calculate the area underneath the curve. And we are able to represent this in terms of integration. Okay, so our bounds are from 0 to 10, and our function is v of t. And because we are integrating with respect to t, we need to include dt there. This is your change in position. Okay, in example 2, we are given the position equation for a car's position, where t is the time in seconds from 0 to 10 seconds. We want to find the position of the car at t equals 0. That means we're just going to find s of 0, and that's going to be 25. So we're just plugging in 0 in for each t, so those 2 terms are gone, we're just left with the 25. And now we're going to find the position of the car at 10 seconds, so that's s of 10. And you're going to plug this in and solve. You should get 475. If you want to find the change of position, we're just going to subtract s of 10 with s of 0, because this is your last position minus your very beginning position. And that's 450. So how does this question relate to the previous example? Okay, well, let's just summarize what we were just saying before. We know that if we take the integral of our velocity equation, we will get our displacement. In other words, the change in position. We also know that s of 10 minus s of 0 is the change in position as well, or our displacement. So if these are the same, we can state that the integral from 0 to 10 of our velocity equation is the same thing as subtracting our position, final position, minus the initial position. So s of t is the antiderivative of v of t. So if we take the derivative of s of t, we're going to get v of t. If I take the antiderivative of v of t, we're going to get s of t. So here is the fundamental theorem of calculus, the evaluation part. So there's two parts, because if we don't have bounds, it's going to be slightly different. So this is the one where we do have bounds from a to b. Then we're going to find the antiderivative of which is f, and then evaluate it by plugging in our b, subtract it with plugging in a into the antiderivative. Here are some following rules. So we know that when we take the derivative of a constant, it's going to be 0. If we take the antiderivative of a constant, we're going to get x, because if I took the derivative of, let's say, 2x, I know that this derivative is just going to be 2. So backwards, the antiderivative of 2 is going to be 2x. And we're going to say plus to constant because, well, what's the derivative of 2x plus 1? It's going to be just 2. But why just 1? It could have been 2. My answer would be the same thing. This could have been a 3, and my answer would still just be 2. So c just represents any constant at the end, because if we take the derivative of the constant, it's going to be 0. Now the power rule. So if you think about the power rule, if I want to take the derivative of x squared, it's going to be 2x. Now, how do I get back to this? So let's just say if I only added a 2 back in here by adding 1 to my previous power. Well, I still don't get x squared. I have 2x squared. So how do I get rid of this 2? Well, I need to divide this by 2 to get this back. And that is what this is describing, this n plus 1 on the bottom. So let's try this with actual integrals that we can integrate. So this first one, we are given bounds for all of these. So we're going to use the fundamental theorem of calculus, the evaluation part, this one right here. So first thing we do is take the derivative of we're going to do the antiderivative first. So the antiderivative of 3 is 3x, and you can always check your work. So what is the derivative of 3x? Well, I should get back 3, and I do in this case. Now we need to evaluate it from 2 to 5. According to the fundamental theorem of calculus, I'm going to plug in the 5 into the antiderivative, and then subtract it by plugging in 2 into the antiderivative. So that's 15 minus 6, which is 9, and that is our final answer. And the next one, the antiderivative of just a 1 is going to be x, and then we're going to evaluate this from 3 to 6. Again, you can check your work. What's the derivative of x? It's 1. So we evaluate it from 6, and then evaluate it from 3 and subtract them. This is 3 as your final answer. This next one is a little bit trickier. So we're going to add 1 to the exponent, but then I also need to divide it by that exponent of 3. Again, you can check your work to see if you get back x squared. So if I bring down the 3, that's going to cancel out in the front, and then I subtract 1 from the exponent, it is certainly x squared. Now we're going to evaluate this from 0 to 3. I'm going to do the 3 first and subtract it with the 0. Now it's going to be gone because that's 0. That's 27 divided by 3, which is 9. Okay, here's the next one. We need to add 1 to our exponent, or in other words, we can say we can add 3 over 3. So if I do that, I'm left with 1 over 3. And then in this case, because I start with a fraction, I need to multiply it by 3. I'm going to ask why. Well, look at the forward direction. Let's say if I want to take the derivative of this. That's 3 times 1/3. And then x of 1/3 minus 3 over 3. So this cancels out and we're left with exactly what we have inside our integral. Okay, now we want to evaluate this from -1 to 8. So that's 3 cubed root of 8 minus 3 cubed root of 1. Sorry, -1. Which is 3 times 2 minus 3 times -1. That's 6 plus 3, which is 9. And that's our final answer. Then for e, got to add 1 to the exponent and then divide by the exponent, which is 4. And we saw it a 5 in the front. Okay, so we're going to evaluate this antiderivative at 2 and then subtract it with 0. Now we're going to simplify. So this is 20 minus 0, which is just 20. Then lastly, I'm going to rewrite this as a negative exponent. So this is the same thing as saying x to the power of -1/2. And I'll take the antiderivative of this. So I'm going to add 1 to -1/2, which is positive 1/2 for my exponent. And then I'm going to multiply this by 2 because I don't want any coefficient in the front for this one. So if I bring down the half is going to cancel with the 2, so I'm left with no coefficient in the front. And then I'll subtract 1 from the exponent, which gives me -1/2 in the exponent. So it works out. So we're going to evaluate this from 4 to 9. So that's 2 root 9 minus 2 root 4. That's 2 times 3 minus 2 times 2, which is 6 minus 4, and that's 2. Okay, so let's look at taking the integral of logs and exponentials. So we know the derivative of ln x is 1 over x. That's why that's your antiderivative for 1 over x. And then we also add a plus c because we could have had any constant in there and it would be the same derivative. So it could have been ln x plus 1. Well, that's still giving me a derivative of 1 over x. Also note is slightly different. You can't forget the absolute value. You can't include the everything. You can't include everything that's in the brackets for that. This one's self-explanatory as well. E to the x is also e to the x when you take the integral of it, because of the derivative of e to the x is e to the x. Then lastly, if we want to take the integral of a to the x, is going to be a to the x ln a, and we know that because if we take the derivative of a to the x, it's going to be ln a to the x. Okay, so we just want to get rid of that ln a, which is why we divided by ln a there. Okay, so let's try this. So 3 is just a number. You can just leave this in the front. And then that means the antiderivative of 1 over x is ln x with the absolute value. And we have to evaluate this from 3 to 6. So that's 3 ln 6 minus 3 ln 3. In other words, if we combine our ln, we're going to get ln of 6 over 3 because we're subtracting according to properties of logarithms. So that's 3 ln 2, and that's our final answer there. Okay, for the next one, again, 2 is just a constant. We could also put that into the front. But once we integrate e to the x, it is still e to the x. We're going to go from -1 to 1. So that's 2e minus 2e to the -1, which is 2e minus 2 over e. And you could just leave it like that. Okay, for the next one, we're going to follow this rule up here. So we're going to have 3x, and our numerator, denominator will be ln 3. It's going to go from -1 to 2. So that's 3 squared over ln 3, subtracted by 3 to the -1 over ln 3. Simplify this just a little bit. That is 9 ln 3 minus 1 over 3 ln 3. And then lastly, I'm going to rewrite this so that our x squared can be on the top. So I'm just going to write this as a negative exponent. The antiderivative of x to the power of -2, I'm going to add 1 to -2, which is -1, and then I'm also going to multiply by a negative because this has to be positive. So again, if I took the derivative of this, that'd be -1 times negative, which is just a positive 1 in the front, and then minus or add and subtract 1 from the exponent here. I'm going to get -2. So we want to evaluate this from 1 to 4, which is, okay, so this is also -1 over x, evaluate from 1 to 4. So this would be -1/4 minus -1, just 3/4. Formulas, we can look at trig functions. So we know the derivative of cos x is negative sine x. But if we want to take the integral sine x, that's negative cos x. And you can look and see all the relationships that should be very kind of familiar to you with maybe just a minus in the front. And we're just going to apply these. And I will give you a library derivative sheet that will be found in your content library, so you can print that out and have access to it. But unfortunately, on the final exam, you still need to have this memorized or just know the relationships between taking the derivative and integrating. Okay, so for this next one, if we take the integral of 1, we're left with x. And then the antiderivative of cos x, if you take a look here, it's sine x. And we need to evaluate this from pi over 2 to pi. So we're going to evaluate this with pi first. So that's pi plus sine pi minus pi over 2 plus sine pi over 2. So that's pi plus 0, because sine pi is 0. And then sine pi over 2 is 1. I'm going to continue to simplify. That's pi minus pi over 2 plus 1. Your final answer is pi over 2 minus 1. Okay, for B, you want to take the antiderivative of secant x tan x, which is secant x. We want to evaluate this from 0 to pi over 4. Okay, so that's secant of pi over 4 minus secant of 0. It's probably easier to write this in terms of cos, so that's 1 over cos of pi over 4 minus 1 over cos of 0. So that's 1 over root 2 over 2 minus 1, which is 2 over root 2 minus 1. Could have a different variation of this by rationalizing the denominator if you wanted to. And then the last type of antiderivative we're going to look at is the inverse trig. So we know that the derivative of sine inverse x is 1 over the root of 1 minus x squared. And the other ones should look familiar as well. These are the main ones we're going to focus on. So this 2 I can just pull out in the front. So this antiderivative is going to be sine inverse x. And we're going to evaluate this from 1/2 to 1. So that's sine inverse of 1 minus sine inverse of 1/2. Sine inverse of 1 is pi over 2. Sine inverse of 1/2 is pi over 6. And if we multiply this 2, we're going to be left with pi minus pi over 3, which is 2 pi over 3. The last one here, we can tell that this is tan inverse of x. But we'll evaluate this from -1 to root 3. So that's tan inverse of root 3 minus tan inverse of -1, which is pi over 3 minus negative pi over 4. So that's going to be 4 pi over 12 plus 3 pi over 12 once we get a common denominator. The last step is to add them together, so that's 7 pi over 12 as your final answer. So you do need to work with inverses when you're doing this. It's kind of like working backwards. It's like tan of what would give us root 3? Well, that's pi over 3. Tan of what would give us -1? That's negative pi over 4. And notice that we are just going to use anything in quadrant 1, or if it's negative in quadrant 4. We don't tend to actually go beyond that, but you could, because the answer it won't be incorrect.